Welcome to Lesson 2.4 GPU Verification Notebook. Learning objectives was 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 was. After completing this lesson, you will create a comprehensive GPU verification notebook. Test model loading and inference on your Tesla P40S. Measure memory usage accurately. Benchmark training speed. Verify multi-GPU detection. Document your system capabilities. What you'll build. A complete Jupyter notebook that 1. Verifies Python and CUDA setup. 2. Tests both Tesla P40 GPUs. 3. Loads models in 4-bit quantization. 4. Runs inference benchmarks. 5. Tests LoRa adapter creation. Generates a system report. Create the notebook. Balays. This command changes the current directory to the specified path where your setup notebooks are located. It's essential to navigate to the correct folder because all subsequent commands and scripts you run will depend on the context of this directory. By using the cd command, you're ensuring that you are in the right place to access the files needed for fine-tuning your language model. After executing this command, you won't see any output, but your prompt will reflect the new directory, confirming that you're set up correctly to continue with the GPU verification process. This command launches Jupyter Lab, which is an interactive development environment for working with notebooks, code, and data. By running this command, you're creating a workspace where you can easily manage your projects and visualize your results. Once Jupyter Lab opens in your web browser, you'll see a user-friendly interface that allows you to create and edit notebooks, run code cells, and access files. This step is essential for verifying that your GPU is recognized and functioning correctly within the environment, as you can execute code that checks GPU availability and performance directly in the notebook. Keep an eye on the terminal output as it will confirm that Jupyter Lab has started successfully, and it will provide a URL to access the interface in your browser. This verification step is crucial before proceeding with fine-tuning your language models. 1. Click plus button. 2. Select Python unsloth kernel. 3. Rename to 00-gpu-verification.ipynb. Notebook contents. Copy each cell below into your notebook. Versus this code snippet sets up a verification notebook to ensure that your Tesla P40 GPUs are functioning properly for fine-tuning tasks. It begins by importing essential libraries like PyTorch for GPU operations, sys for system-specific parameters, and psutil for system monitoring. The platform module helps in gathering information about the operating system, which is crucial for compatibility checks. The display settings from IPython allow for better visualization of outputs, while the warnings filter suppresses any unnecessary warning messages during execution. When you run this code, you'll see the message "Galilei import successful" printed in the output, confirming that all necessary libraries have been loaded without issues. This step is vital because it ensures that your environment is correctly set up before you proceed with any GPU-intensive tasks. This Python script provides a comprehensive overview of your system specifications, which is essential for verifying that your environment is set up correctly for GPU utilization. It begins by printing a header to clearly delineate the system information section. Next, it retrieves and displays details about your operating system, including the platform name, version, and machine type, which helps confirm compatibility with the software you will be using. Then it checks your Python environment, showing the version and executable path, ensuring that you're running the correct Python version for your project. Finally, it uses the psutil library to gather memory statistics, displaying total available and used memory. This information is crucial for understanding your system's capacity and ensuring it can handle the demands of fine-tuning large language models. After running this script, you'll see a clear summary of your system specs, confirming that everything is in order before proceeding. This Python script is designed to check the versions of critical packages needed for fine-tuning LLMs with unsloth. It begins by printing a header to clearly delineate the output. The script defines a list of essential packages, including PyTorch and transformers, which are foundational for model training and manipulation. Within the loop, it attempts to import each package and retrieve its version. If successful, it prints a confirmation with a checkmark and the version number. If a package isn't installed, it catches the importee and indicates that with a crossmark. This step is crucial because ensuring you have the correct package versions installed can prevent compatibility issues down the line. The final output will give you a clear overview of what's installed and what might need attention. This Python code snippet is designed to verify the availability of CUDA and detect any GPUs on your system. First, it checks if CUDA is available, which is crucial for utilizing GPU resources for training models. If CUDA is not available, the output will clearly indicate that with a warning message preventing you from attempting GPU training. If CUDA is available, the code will display the CUDA version and the cuDNN version, as well as whether cuDNN is enabled. This information is important because it confirms that your environment is set up correctly for deep learning tasks. Next, the script counts the number of GPUs detected. If GPUs are present, it provides detailed information about each one, including the GPU name, compute capability, total memory, and current memory usage. This output helps you understand the resources at your disposal for model training and optimization. This Python script is designed to test GPU memory allocation, ensuring that your setup can handle the required resources for fine-tuning large language models. The function test_GPU_memory takes a device ID and a size in gigabytes, calculating the number of elements needed for a square tensor based on the specified size. When you run this script, it attempts to allocate approximately 2 GB of memory on each available GPU. If successful, you'll see a success message along with the actual memory used, confirming that the GPU is functioning correctly. If there's an issue, an error message will indicate the failure. After the test, the script cleans up by deleting the tensor and emptying the cache, which is crucial for maintaining optimal performance. Finally, the script loops through all GPUs, allowing you to verify each one. This step is essential before proceeding with intensive tasks like model training. This code benchmarks the computation speed of your GPU by performing matrix multiplication. It starts by printing a header to clearly indicate that you're running a GPU computation benchmark. The function benchmark_matmul is defined to take in parameters for the device ID, matrix size, and number of iterations. Inside the function, it initializes 2 random matrices on the specified GPU and performs a warm-up run to ensure the GPU is ready. The actual benchmarking occurs in a loop where it measures the time taken for each matrix multiplication and synchronizes the GPU to ensure accurate timing. After running the specified iterations, it calculates the average time and computes the performance in TFLOPS, which is a measure of how many trillion floating point operations the GPU can perform per second. The results for each GPU are collected in a dictionary and printed out, giving you a clear view of your GPU's capabilities. This step is crucial for ensuring that your hardware is ready for fine-tuning LLMs effectively. This code snippet is designed to test loading a language model using 4-bit quantization, which is a technique that reduces the model's memory footprint while maintaining performance. It begins by cleaning up any residual memory using garbage collection and clearing the CUDA cache to ensure a fresh start. Next, it loads the Qwen 2.5-0.5b-instruct model specifying the 4-bit quantization flag. This is crucial as it allows the model to operate efficiently on limited GPU resources. After loading, the script calculates the memory used by the model and displays both the model's memory usage and the total GPU memory allocated, confirming successful loading. It also provides insights into the model's parameters, including total, trainable, and frozen parameters, which are important for understanding the model's complexity and training potential. If loading fails, an error message will be displayed, helping you troubleshoot the issue. This step is essential in verifying that your setup is correctly configured to handle model loading and quantization. This Python code snippet is designed to test the inference capability of a language model. First, it checks if the model is loaded. If not, it alerts you that the inference test will be skipped. When the model is available, it prints a header to indicate the start of the inference test. The code then enables inference mode, which optimizes the model for generating responses. It sets up a test prompt asking, "What is 2 plus 2?" and tokenizes this input. The tokenization process prepares the text for the model by converting it into a format it can understand, and the output confirms the number of tokens generated. Next, the model generates a response based on the input, measuring the time taken for this operation. After generating the output, it decodes the response back into human-readable text. Finally, it displays the model's response, the number of tokens generated, and the processing speed in tokens per second, providing valuable insights into the model's performance. This Python code snippet tests the addition of LoRa adapters to a language model, which is crucial for efficient fine-tuning. First, it checks if the model is loaded. If not, it skips the test. When the model is available, it prints a header indicating the start of the LoRa adapter test and specifies the parameters being used, such as the rank and alpha values, as well as the target modules for adaptation. The core functionality is wrapped in a try-except block to handle any potential errors gracefully. The model is updated using the get_peft_model method, which adds the LoRa adapters with specified parameters, including dropout settings and the random state for reproducibility. After adding the adapters, the script calculates and displays the total number of parameters, the number of trainable parameters, and the percentage of trainable parameters. It also checks the GPU memory usage, confirming the memory allocated after adding LoRa. This output is essential as it highlights the efficiency of LoRa, allowing you to train only a small fraction of the model's parameters while still achieving effective results. If there's an error during the process, it will notify you accordingly. This Python script is designed to test the maximum model sizes that can be loaded into your GPU memory. It starts by cleaning up any existing models and freeing up memory to ensure accurate testing. The script then defines a list of models with varying sizes, which is crucial for evaluating your GPU's capacity. As it iterates through each model, it attempts to load it while measuring the memory used. The load in 4-bit =true option allows for efficient memory usage, which is particularly important for larger models. If the model loads successfully, it prints the memory used and the percentage of total memory utilized, confirming that the model fits within the GPU's limits. If a model is too large, it captures the error and notes that it didn't fit. Finally, the script summarizes the results, showing which models fit and how much memory they required. This information is vital for planning your projects and ensuring that your GPU can handle the models you intend to work with. This Python script generates a comprehensive system report that helps verify your GPU's capabilities for fine-tuning large language models. The report begins by printing a header and then gathers essential system information, including the operating system, Python version, PyTorch version, and CUDA version. The script checks if CUDA is available and retrieves details about each GPU in your system, such as the total VRAM, compute capability, and the number of multiprocessors. This information is crucial as it directly impacts your model training performance. Finally, the report provides tailored recommendations based on the GPU specifications, indicating which model sizes are feasible for training. This guidance helps you optimize your resources and avoid running into memory issues. When you run this code, you'll see a neatly formatted output that confirms your system's readiness for the task ahead. max_seek_length =2048 per_device_train_batch_size =2. This step is crucial for verifying that your GPU is correctly set up to handle 13B models. By running this command, you're ensuring that the necessary resources are available for efficient model training and inference. When executed, the command will check the GPU's memory and compute capabilities, confirming that it meets the requirements for handling larger models like the 13B variant. Pay attention to the output, which should display details about your GPU specifications and available memory. If everything checks out, you'll see confirmation that your GPU is ready for the task ahead. If there are any issues, this output will help you identify what needs to be addressed before proceeding with fine-tuning your model. max_seek_length =1024 per_device_train_batch_size =1. This code snippet is generating a report confirming that your system is properly configured for fine-tuning. The first part prints a status message indicating that everything is ready for training, which is crucial for ensuring that your GPU setup is functioning as expected. Next, the report is saved to a markdown file named gpu_verification_report.md. This is important because it allows you to keep a record of your system's verification status for future reference. After saving, the code outputs the absolute path of the report file, so you know exactly where to find it. Finally, a line of equal signs is printed to visually separate this output from any subsequent messages, making it easier to read. This step ensures you have a clear confirmation of your setup before proceeding with fine-tuning. This code snippet is designed to clean up and free any GPU memory that may have been allocated during your previous operations. First, it attempts to delete the model and tokenizer objects, which helps in releasing their memory. The try except block ensures that if those objects don't exist, the program won't throw an error. Next, it forces garbage collection using Python's GC module, which is a crucial step to reclaim memory that is no longer in use. Following that, the write torch.cuda.empty_cache function is called to clear any cached memory held by PyTorch, making it available for future. Finally, the code checks the memory allocated on each GPU and prints the results, confirming that the cleanup was successful. You'll see the memory usage for each GPU, which should ideally show reduced memory after cleanup. The completion messages indicate that your system is now ready for the next steps in fine-tuning. Running the notebook. Option 1. Run all at once. Menu, run all cells, or Shift+Alt+R. Option 2. Run cell by cell. Click in each cell. Press Shift+Enter. Review output before continuing. First run, 5-10 minutes, downloading models. Subsequent runs, 2-3 minutes. This output indicates that the GPU verification process has been successfully completed. It confirms that your system is properly configured and ready for fine-tuning large language models. Ensuring that your GPU is functioning correctly is crucial as it significantly speeds up the training process compared to using a CPU. The message also prompts you to move on to the next lesson, where you will begin test training. This is an exciting step as it will allow you to apply what you've learned so far and see the model in action. Make sure to take note of any additional information provided in the next lesson to optimize your training experience. Understanding your results, model size, DR bit memory, recommended batch size, DR bit memory, recommended batch size, DR bit memory, DR bit memory, recommended batch size, 0.5b tilde 0.5 GB, 6 in, vertical bar 78b, vertical bar approximately 8 minus 10 GB, vertical bar 2, vertical bar 13b, vertical bar approximately 14 minus 16 GB, vertical bar 1, expected Tesla P40 performance, matrix multiply 5 minus 7 TFLOPS FP32 and Ference speed 20 minus 40 tokens slash second 7B model, training speed approximately 2 seconds slash step 7B batch equals Wi-Fi TCC mode enabled. Check temperatures, thermal throttling, troubleshooting. This code snippet modifies the GPU memory test by changing the allocated memory size from 2.0 GB to 1.0 GB. This adjustment is essential for ensuring that the test runs smoothly on systems with limited GPU resources. By reducing the memory requirement, you minimize the risk of encountering out-of-memory errors, which can halt your fine-tuning process. After executing this command, you should see output indicating whether the GPU memory allocation was successful. A confirmation message will assure you that the GPU is functioning properly and is ready for the next steps in your model fine-tuning journey. Solution: check internet connection, try again. This comment indicates that the model download process is resilient. If your download gets interrupted for any reason, it will automatically resume from where it left off when you rerun the command. This feature is particularly useful when dealing with large model files, as it saves time and bandwidth by not requiring a complete restart of the download. Ensuring that your model can resume downloading is essential for maintaining efficiency, especially in environments with unstable internet connections. This small detail can make a big difference in your workflow, allowing you to focus on fine-tuning your model without the hassle of repeated downloads. Solution: this is a known unsloth/bits and bytes issue on some systems. This code snippet is responsible for generating text using your fine-tuned model. The write single quote model.generate write single quote function takes the inputs you've prepared and produces new tokens based on them. The max_new_tokens parameter specifies that you want to generate up to 50 new tokens, which helps control the length of the output. Setting do_sample to false means you're opting for greedy decoding, where the model will always select the token with the highest probability at each step. This approach can lead to more coherent outputs, especially for tasks requiring precision. After running this code, you'll see the generated text in the output. This output confirms that your model is functioning correctly and is capable of producing meaningful continuations based on the input you've provided. Verification checklist. Vatyu Consec. Thus, you'll master these techniques quickly. After running the notebook, verify Manispet both Tesla P40 GPUs detected. Manispet 24 GB VRAM available per GPU. Manis model loads in 4-bit, hence UGB for 0.5B model. Miference works and generates text. Mi for LoRa adapters add successfully. Mi for Lizosut varezot velekotivok want vatetutul. Mieste 7B model fits in memory, approximately 8 mifotot detect mifotot. System report saved. Minus all cells run without critical errors. All checked. Your GPUs are ready for training. Key takeaways. 1. Both GPUs work independently. Can train on either one. 2. 24 GB is enough for 7-8P models with QLoRa. 3. 4-bit quantization saves 75% memory compared to 6. LoRa reduces trainable params to 1% massive efficiency gain. 5. Tesla P40 is capable minus good performance for fine-tuning. 6. Monitor memory always. Use torch.cuda.memory_allocated. 7. Clean up between. Next lesson. GPU verification complete. Next, lesson 2.5, first test training. In the next lesson, you'll run an actual training session, just a few steps, to verify everything works end to end. Save this note. You'll use it to benchmark performance and troubleshoot issues throughout the course. This image displays the VRAM usage by different operations when fine-tuning a 7 billion parameter model on a Tesla P40 GPU. We can see that loading the model in 4-bit format uses approximately 8.5 gigabytes of VRAM, while the training process using LoRa requires the most memory at 14.2 gigabytes. Inference, or generating outputs from the model, uses about 9.3 gigabytes of VRAM. Understanding these VRAM requirements is crucial for optimizing your workload, especially when dealing with limited GPU memory. Knowing that the Tesla P40 has a total of 24 gigabytes of VRAM, it's important to manage your resources effectively to avoid running out of memory during training or inference. Next, you should ensure you have adequate VRAM available for your specific use case, particularly if you're planning to explore more complex models or larger batch sizes. This knowledge will help you streamline your fine-tuning process, maximizing performance while staying within your system's limits. Here we have the specifications for the Tesla P40 GPU, which is essential for understanding its capabilities in our fine-tuning tasks. The architecture is based on the Pascal design, specifically the GP102, with 24 GB of GDDR5 VRAM. This GPU can handle substantial data loads, allowing for efficient processing in machine learning applications. Next, the P40 is equipped with 3840 CUDA cores, which significantly boosts parallel processing potential. This is complemented by a compute capability of 6.1, indicating its ability to run complex operations efficiently. Looking at performance, the FP32 performance is rated at an impressive 12T FLOPS, making it powerful for intensive computations. The memory bandwidth of 346 GB per S also plays a critical role in ensuring data can flow quickly between the GPU and memory, reducing bottlenecks during processing. Additionally, the thermal design power is rated at 250 watts, so it's important to ensure proper cooling in your setup. Released in 2016, this GPU remains a reliable choice for data center applications. Understanding these specifications will help you maximize the performance of your model fine-tuning. Next, make sure your setup meets these requirements before proceeding. This image illustrates the VRAM usage for training versus inference in a neural network. On the left, we see the breakdown of VRAM usage during the training phase. Here, model weights constitute 40% of the total VRAM, while optimizer states and gradients account for 30% and 20% respectively. Activations take up the remaining 10%. Altogether, this gives a total VRAM requirement of about 14 gigabytes during training. Now, if we look at the right side for inference, we notice a significant shift. The VRAM usage drops to approximately 9 gigabytes, with model weights occupying the entirety of that memory, or 100%. This is because inference does not require gradients or optimizer states, leading to a much leaner memory footprint. Understanding this distinction is crucial, especially when optimizing resources for different stages of your model's life cycle. For your next steps, consider how these VRAM requirements may affect your training strategy and deployment to ensure you're optimizing for both performance and resource allocation. This knowledge will help you make informed decisions as you fine-tune your models. This image displays a comparison of GPU training speeds for different models when fine-tuning a 7 billion parameter model using the LoRa technique. The chart presents the performance in tokens generated per second across various GPU options. You can see that the RTX 3060 with 12 GB of memory has the lowest performance, managing only 950 tokens per second. The Tesla P40, equipped with 24 GB, offers a moderate improvement at 1800 tokens per second. Looking at the higher-end GPUs, the RTX 4090 achieves 3200 tokens per second, providing a noticeable boost. Finally, the A100, boasting 40 GB of memory, tops the list with an impressive 4500 tokens. Understanding these differences is crucial for optimizing your setup. If you're working with limited resources, the Tesla P40 might be a suitable entry point, but for more demanding tasks, the RTX 4090 or A100 would significantly enhance training speed. As you progress in your fine-tuning journey, consider how these benchmarks can inform your choice of hardware. Next, make sure to explore how to set up your environment to fully leverage the capabilities of your chosen GPU. This image illustrates the CUDA software stack, which is crucial for running your training scripts effectively on your Tesla P40 GPUs. At the top, we have your application layer, which is essentially your training script. This is where you'll implement your model and handle the training process. Beneath that is the framework layer, where you'll choose between PyTorch or TensorFlow. Both frameworks are popular for deep learning and provide the tools needed to utilize CUDA capabilities. Next, we see the CUDA runtime, referred to as CUDA. This plays a vital role in managing memory and executing kernel functions on the GPU. It ensures that your application can communicate effectively with the GPU hardware. Then we move to the CUDA driver API. This layer operates directly with the GPU driver, handling lower-level operations and configurations necessary for proper execution. Finally, at the bottom, we have the hardware layer with the Tesla P40 GPU, which provides the processing power needed for your deep learning tasks. Understanding this stack is essential as it helps you identify where potential bottlenecks might arise during implementation. As you progress, ensure your setup aligns with this stack. This knowledge will be foundational as you dive deeper into fine-tuning LLMs using the Unsloth library. This image presents a training memory allocation map for a 7 billion parameter model. It breaks down how the GPU's memory is distributed during the training process. Notably, model weights occupy 40% of the memory, which is significant since these parameters are the core components your model learns from. Gradients, which are essential for optimizing the learning process, take up 20% of the allocation. You need to monitor this closely as gradients fluctuate throughout training, impacting your performance tuning. Optimizer states, which help in fine-tuning the weight updates, comprise 30% of the memory. Lastly, activations, necessary for storing intermediate results during forward passes, represent only 10%. Understanding this breakdown is crucial for effective GPU resource management as it allows you to make informed decisions about memory usage and optimization strategies. As you move forward, keep these percentages in mind when configuring your training settings to ensure you're maximizing GPU efficiency.